This is my kinematics demonstration where I'll compare different types of projectiles. I'll explore the properties of a projectile with only a vertical component and another projectile with a horizontal and vertical component. For this experiment, I'll be using a green screen with 30 centimeter markings in order to determine the velocity and double check our work. The table that I had to fight for to use, a makeshift lighting rig that I made, a camera stand centered in the middle of the lighting rig, my phone 240 recording at 240 frames per second in order to capture some slow-mo footage, and finally a Trix 101A skateboard wheel with a diameter of 52 millimeters and a weight of 200 grams. I use a skateboard wheel because it has one of the simplest shapes that I can use, which is a circle, and this will minimize drag as much as possible. And also because the wheels are designed to conserve as much momentum as possible, which will help us get consistent results. To set up the experiment, I first made 30 centimeter markings on the green screen, a trick that you learned from Mythbusters. We can use the markings in order to determine the displacement of the wheel relative to its time and double check if the wheels are actually falling at the same time. I then hung up the green screen on a wall and placed a table right in front of it. I then measured the center of the trajectory of the wheels in order to get the most accurate results. I centered the lighting on the measurements and then later centered the camera for my experiments in order to yield the best results. I then did a few practice runs in order to find out where each ball would land. I adjusted my camera angles and my lighting depending on the trajectory of the wheel and determined a rough estimate of how hard I should push the second wheel. And finally, I pressed record and began to get some data for my demonstration. My thought process for the demonstration was that I knew that theoretically both projectiles should land at the same exact time frame, but there are too many factors at play that will allow for this. I thought maybe the horizontal trajectory of the second projectile might cause the wheel to gain some kind of lift, resulting in it falling slower. The rotation of the wheel might have a larger effect on the ball than what I might have expected. So in order to make sure, I double checked my work by the 30 centimeter markings on the green screen. I did this because at first glance they might seem as they're falling at the same time, but I wanted some quantifiable evidence I can compare each run with. For the experiment, I had 10 run for each type of projectile. The times for how long each projectile ranged from 350 to 400 milliseconds on both types. What I did in order to find the ideal and most consistent trajectory was to isolate each of the frames of each run and began to eliminate outliers. I did this excruciating process for all 20 runs. I finally ended up with the run that illustrated the perfect trajectory. I then looked frame by frame and determined at what frames does the wheel start moving and when it hits the floor. I calculated the times of each run and here are my results. So in conclusion, we can roughly prove that in the real world, a skateboard wheel dropped with no horizontal velocity will fall slightly faster than a wheel with a horizontal trajectory. Even though the difference is 5 milliseconds, there's still a difference that has been affected by some sort of variable. The wheel might have been bouncing on the table. These bounces would be very small but could have an effect down to the millisecond, which might be what we see. This could be due to the spin of the wheel that might create regions of high and low pressure that might affect its descent, which would be an excellent segue into our next unit. Finally, in order to double check our work, the wheel with no horizontal speed traveled 79 centimeters vertically in 383 milliseconds, giving it a final velocity of 2.063 meters per second, and the wheel with a horizontal trajectory traveled 80 centimeters vertically in 388 milliseconds, giving it a velocity of 2.062 meters per second. This 0.001 meters per second difference is where the real life physics operates in.